getting back to types of chemical reactions. We talked about chemical reactions a little bit. We say, this occurs and this makes this, and you have to balance both sides. But we haven't really talked about what kinds of chemical reactions there are, or how to actually know whether a chemical reaction has taken place. For instance, there's something wrong in this picture right here. It says types of chemical reactions, and then what reaction is that you're looking at?
Combustion?
Anyone know what that is? It's not combustion.
Wasn't it nuclear fission?
It's a nuclear, yes, exactly. It's a nuclear reaction. It's not a chemical reaction at all. So that was sort of one of those things that we haven't really made the difference. This reaction involves neutrons, not electrons. So it's not a chemical reaction. It's actually a nuclear reaction. And we're not really going to talk about those very much. You can later on. It's a very interesting topic, of course. But yeah, that is a nuclear reaction. So how do we know when a chemical reaction's taken place? I mean, this has been, people have been looking at things changing for, tens of thousands of years and trying to figure out how something was there at the beginning, something was dropped on it, or it fell into a liquid or something, and then something happened to it. How do you actually know that a chemical reaction took place rather than a physical reaction, like ice melting was on the test? That was the only physical reaction. Everything else was chemical. For instance, just dropping salt into water is a chemical reaction because you're breaking an ionic bond. So anytime you break a bond or form a bond, that's a chemical reaction. That doesn't occur when ice melts because you've got water before and you got water after. Now, some ways we can see that an actual chemical reaction has taken place is just by looking with our eyes, feeling with our hands. Color change is a classic determination that a chemical reaction's taken place. And one of the really interesting things I just sort of watched a video about the other night involved alchemy. And what was the main thing that alchemists were trying to do? Do you remember there was really one reaction they were really trying to do? Anyone remember what it is?
I think they were trying to turn into gold. So anything into gold.
Exactly. Yeah, they were trying to turn lead into gold because, lead is fairly common and it's heavy. And gold is not so common and it's worth a hell of a lot more. And it's also heavy. And I learned that one of the reasons why alchemists may have thought they were onto something was because one of the reactions that you do with lead is if you add iodine to it, you form lead iodide. And lead iodide is a very bright yellow color. And when it dries, it looks like gold flakes. It actually really looks like it. And so I think that was the impetus for alchemists thinking, well, I've made gold. I've taken lead. It's now in solution. I've added another solution to it. It's turned it into gold because it really does look like gold. And that is one of the key signs of a chemical reaction. As you can see with this test tube on the right, what's happened is that a precipitation reaction has taken place. You formed something, and that's also something you want to look for. You have formed, in this instance, a solid. Down below, in this instance, you have formed a gas. Something new is present that wasn't there before. So you change colors. You may not form a precipitate or a gas, but you've changed colors. So something new is present that wasn't there before. Heat is released. Heat is either released or absorbed. That happens as well. Like if with some salts, for instance, if you dissolve certain salts into water, they take up heat and they get really cold. That's how ice packs work. When you break an ice pack basically there's water on one side of a membrane and there's salt on the other side of the membrane. And when you break the membrane, they come together, the salt dissolves in the water and it absorbs heat from the outside. That's a chemical reaction. So you make a gas, you see bubbles. You have a solution, you see bubbles forming. That's a reaction. Or you see these fumes. Like here, it looks like they're burning some magnesium wire, which is a really fun reaction to do. We would have done that. I always love doing that because it's just this intense light when you burn magnesium ribbons, but it releases fumes. Or you form a solid, such as a precipitate, or the reaction we looked at in the last class. Actually, I don't know if we looked at it in the last class. We'll look at it in this class. When you have an oxidation reduction, where you have a metal in solution and a solid metal, and they switch electrons, and the metal that was in solution becomes a solid, and the metal that was a solid goes into solution. Basically, that's also a classic chemical reaction and an oxidation reduction reaction as well. So what does oxidation reduction mean? We say redox because basically it's a shorthand for reduction and oxidation, because I guess ox-red sounds weird. Redox is easier to say. So that just involves the transfer of electrons basically from one atom to another atom, and it changes its oxidation state or its oxidation number. So when electrons are lost by an atom, we say they have been oxidized. And I think you can probably guess why we call it that, because a lot of the time they're losing those electrons to oxygen. And you can see that when we were balancing, we were calculating oxidation numbers. Oxygen was always -2, right? Pretty much always -2. So when oxygen is by itself, just the oxidation, when just oxygen molecule that we breathe in, what's the oxidation number of oxygen when it's in a molecule?
0.
Yeah, it's 0. Yeah, that's one of the rules. There's a lot of rules to go over for redox reactions, but that's one of the rules, is that any element in its most stable form, its oxidation number is 0. So like O2, N2, F2, Cl2, all of these gases that are molecules, diatomic molecules, they all have oxidation numbers of 0. And so you can see basically when oxygen reacts with anything, with the exception of fluorine, its oxidation number goes down. It goes from 0 to -2. And so we say that oxygen has been reduced because its oxidation number has been reduced. The weird thing to think is that it's actually gained electrons. So we say it's gained something, so it's been reduced. That's confusing for a lot of students. But if you just think about its number, has its oxidation number been reduced? And the answer is yes. And basically anything that the oxygen has reacted with, its oxidation number has increased. It's gone up. So the opposite of reduction, it's actually increased. So here's classic oxidation reduction reaction is right here, looking at these old rusty tools. So you've got iron, which is, somewhat shiny solid, and you leave anything made out of iron in the presence of oxygen for an extended period of time. This oxidation reduction reaction is going to take place because oxygen really likes electrons. Remember, this has a lot to do with electronegativity. And electronegativity, anyone can remind me what electronegativity means? If something's electronegative, what does that say about that element?
it wants to gain more electrons to be a noble gas.
Well, remember electronegativity, we measure electronegativity when something's already in a bond.
Okay.
So you're really close with that. But if something's very electronegative, what does it do?
It's pulling the electron more to its side.
There you go. Exactly. Yeah. It means if it's in a bond, so if I have oxygen here and iron here, it means that oxygen is pulling those electrons away from the iron. And basically, the electrons are spending more time close to the oxygen atom than they are the iron atom. And so what we can say is that those electrons basically belong to oxygen now, because they're more near oxygen than they are near iron. So iron has gone from a place when it was a metal to strictly a metal, whereas freely sharing electrons in metallic bonds, now it's reacted with oxygen, and oxygen is now, instead of freely sharing electrons, it ain't freely sharing electrons anymore. It's pulling those electrons toward itself. And iron is actually being left with basically a charge. So if we look at what would be the oxidation number of iron here? On the left side, iron is a metal. What would the oxidation number of iron be? So this one right here. What would the oxidation number of iron be over there? Raymond knows. Remember, it's an element in its most stable form. What's its oxidation number going to be? It's the same for all elements in their most stable form.
0.
Yeah, 0, none. Basically, what it means is that any element in its most stable form is freely sharing electrons back and forth with other atoms that are identical to itself. Like if I have a bar of iron, every iron atom in that bar has the same electronegativity. And so those electrons are going to be freely shared. Same with oxygen. So that's going to be 0. That's going to be 0. Because the oxygen element, which looks like this, right? It has 2 bonds. So there's 4 electrons, and they're being pulled equally by each oxygen atom. And so the electron density around this oxygen is exactly the same as the electron density around that oxygen. They're both identical. And so because of that, the oxidation number is 0. When the electron density gets pulled towards one atom and away from the other, then the oxidation numbers change. And that's what happens here. So now when we look at rust, this is basically rust. What are the oxidation numbers now? What's the oxidation number of oxygen now?
-6.
Excuse me?
-6.
-6 for all 3, right. So we would have a total of -6. What would be the oxidation number for 1? Hey, Jerome, come on up here. Good Lord. So what would be the oxidation number for 1 of the oxygens?
-2.
Right. So oxygen has now gone to -2. And what about iron? What's the oxidation number of the iron now?
+3 for one of them. +6 for the total.
Perfect. Yes, exactly. So that's iron 3 oxide. And the 3, anytime you see a Roman numeral, that's an oxidation number. Because the oxidation number of an ion is the charge in the ion. So that is iron 3 oxide. that's a giveaway to what the oxidation number of the iron is. It's 3. Because it has a +3 charge, that's also its oxidation number. So we can see that 6 electrons have moved in this reaction. 6 electrons have gone from iron to oxygen. Iron has been oxidized, and those 2 atoms have lost a total of 6 electrons, and those 3 oxygen atoms have gained a total of 6 electrons. And so when we balance oxidation reduction reactions, we have to balance the atoms and we have to balance the electrons, because everything has to balance. The charge, the atoms, and the electrons all have to balance, and we'll learn how to do that.
Professor,
Yes.
how do we get the oxidation numbers without drawing the structure? Like, how did you get it so fast? Or do we have to?
Oh, oxidation numbers in ionic compounds are fairly straightforward because we don't really need to. Will, you're on. Sure, come on up. Man, you're being a pain today, buddy. So oxidation numbers in ionic compounds are relatively straightforward because they're all charged. And so we know what the oxidation numbers are going to be. Oxygen has a -2 charge, therefore its oxidation number is -2. Iron has a +3 charge, therefore its oxidation number is going to be +3. It gets a little trickier in covalent compounds. And one of them was in the recitation we did on Tuesday. It was, let me draw. Remember, it was this one. Whoops. And so we had 2, this was dinitrogen trioxide. And when we look at the, we have to draw this out to see what the oxidation numbers are, because this nitrogen and this nitrogen are in different circumstances. One is bound to a single oxygen, the other is bound to 2 oxygens. And so anytime you're bound to more oxygens, your oxidation number is going to be increased because oxygen takes electrons from you. So in this instance, one of the nitrogens I think is +2 and the other one is +4. So when it's a covalent compound, it sometimes really helps to draw everything out and see because not all of the atoms will be in the same situation. Okay, so ionic, fairly easy. Covalent, sometimes a lot trickier.
Okay, thank you.
So yeah, so I would recommend actually when you're doing these sort of things, if it's a covalent compound, to actually draw the Lewis structure. Because one of the things we need to do when we're balancing oxidation reduction reactions, we actually need to know who's being oxidized, who's being reduced. That's the whole point, because we need to know how much oxidation and how much reduction is taking place so we can balance the electrons going in one direction and the electrons going in the other direction. So yeah, so we need to identify what's going on. In ionic reactions, not that hard. When they're non-ionic reactions, yeah, they're a lot more difficult. So again, just to sort of makes the point of how do you identify an oxidation and how do you identify a reduction. So here is a classic oxidation reduction reaction. Actually, you can make a battery with this reaction, and all batteries. Hey, man, these two are testing my patience this morning. All batteries work on oxidation reduction reactions because you're transferring electrons from one place to another. And it's that transfer of electrons from one place to another that allows us to power things. So basically we just hook up a wire and those electrons go from the reduction all the way through balancing whatever, or sorry, goes from the oxidation reaction. The wire transfers those electrons all the way around to the reduction part. And we power, whatever, our car, our radio, our watch, whatever it is, by the transfer of those electrons. So here I've got zinc. And remember, zinc, when it's by itself, it's in its most stable state. So what's its oxidation number going to be?
Zero.
Zero. It's always going to be zero. Hopefully that's one of the easier things to remember, that when atoms are basically surrounded only by other atoms exactly the same as themselves, then they're not going to be losing electrons or gaining electrons in the net sense. Electrons are going to be shared nicely, shared equally. But when it goes into solution, and that's what aqueous means, remember, it goes into a water solution, we know that now it's charged because ions are soluble in water and the metal is not. And so when we have an ion going into solution, that is, when it's a metal, it's because it's lost electrons. So what's its oxidation number when it's an ion?
+2.
Yeah, that's its charge. That's right. If its charge is +2, its oxidation number is +2. If it was an aluminum ion with +3, its oxidation number would be +3. And so we say that zinc has been oxidized because, and this is like one of the mnemonic devices for you to remember which is which. Oxidation is the loss of electrons. So oil, OIL, oxidation is loss. On the other hand, copper, when it's in solution, one of the charges it has is +2, one of the common charges of copper. You're going to have to lie down, buddy. Okay? Yeah, there you go. So when it's in solution, it's +2. So its oxidation number is +2. Now, those 2 electrons that were lost by zinc go to the copper ion, and it gets reduced. So the copper goes from +2 back to 0, and now it becomes a solid metal again. And so we say reduction is gain of electrons. So if you're ever wondering which is which, oil rig is one of the memory devices that people can use. Oxidation is loss of electrons. Reduction is gain of, just remember, it's of electrons. And so this would be a full oxidation reduction reaction where zinc gets oxidized and loses 2 electrons, and then those 2 electrons get transferred to copper ion in solution. It becomes solid again. It becomes reduced. So that is a balanced reaction. We have zinc on one atom of zinc on one side, 1 atom of zinc on the other side, 1 atom of copper on one side, 1 atom of copper on the other side, and 2 electrons, 2 going into the reaction and 2 coming out. So that's a balanced redox reaction. To just give you an idea of other things that take place, like when we throw sodium into water, we all know that goes boom. It's fun. That's an oxidation reaction because it goes from oxidation number of 0 to +1, and then an electron is released. One thing I want to point out is at the bottom, notice that iron +2, can be oxidized again to iron +3. So what is it about iron that allows it to do that? What kind of atom is iron? It's a specific kind. What's different about iron and say sodium and calcium here. When sodium gets oxidized, it goes to +1. When calcium gets oxidized, it goes to +2. That's it. Those are the only two reactions that take place. But when iron can get oxidized to more than one different form. Why is that?
Transition metal.
Bingo, exactly. It's a transition metal. That's what it being a transition metal means. It means that you can lose more than one number of electrons. And in iron's case, it can lose 2 or 3. And so even when iron's at a +2, it can be oxidized even more and that's what will happen in the presence of oxygen. It can first go to just FeO, it's for iron 2 oxide, and then it can be oxidized even further to Fe2O3. So it goes from iron 2 to iron 3 fairly quickly. Oh. Come on. Why won't it let me
Professor?
go to... Yes.
So does the oxidation number have to do with how quickly something hydrolyzes?
Hydrolyzes. Hydrolyze is a very specific term, meaning a bond gets broken by water. So it's not quite the same thing, but the electronegativity is definitely involved in that. Yeah, we'll see how electronegativities are involved big time in these reactions because it determines who's going to get the electrons. And I'll show you a few reactions that explain that. But yeah, hydrolysis means bond broken by water. It's a very specific chemical meaning.
Okay. Thank you.
So here's the zinc to copper reaction again. So here we've got copper ion in solution. So here's our copper ion in solution, and it's with chlorine or something, chloride. So there'd be other ions in there, chloride ion or nitrate ion or some other ion in there. But the copper goes to the surface of the zinc, and when it hits the surface of the zinc, it is more electronegative than the zinc. That's the key. If something's more electronegative, basically it means that it pulls on electrons better than the other atom. Copper pulls on electrons more than zinc does. And so it pulls those 2 electrons away from the zinc and it goes to the copper. Now what happens is the copper now becomes a metallic atom again. It is no longer an ion. It's now a metallic atom. And the zinc, it basically takes the place of that zinc atom that it took the electrons from. And now the zinc atom becomes ionized and is now in solution. So 2 electrons have basically changed hands from the zinc to the copper. And so what happens is you can see this reaction take place. It's a fun reaction to do. We actually do it with aluminum foil in the lab, and I'll show you that one. So we get a nice, pretty blue copper 2 solutions of this really pretty blue color. And so here we've got copper ion in the solution, and here we've got a solid piece of zinc. So what happens when you just drop the solid pieces, you don't even have to do anything, just drop the solid piece of zinc into the copper solution and wait. And what happens, you can see what happens here. I don't know if you can see it very well, but look at the surface of the zinc now has this really dark orangey brown, I don't know if you call it film on it. That's copper. So copper, what you're doing here is copper plating. And you've probably heard of like electroplating before, like things get chrome, like bumpers. If you have like a really old car, they'll re-chrome it. basically what they do is electroplate the bumper. They'll just drop the whole bumper into a solution containing chromium and put an electric current through that solution, so that chromium will be reduced. And so the chromium ions will then go from the solution to your car bumper and make them all nice and shiny again. And same thing here, though we don't have to add any electricity because this happens all on its own. So the zinc gets oxidized and the copper goes from being the nice, pretty blue ionic color to that sort of, dirty orange, brownish film on the zinc. It gets reduced, okay? So these are a couple of terms that we're going to use that sometimes are confusing to think about, because what we're going to talk about is an oxidant or an oxidizing agent is what gets reduced. It's like, if I have something that's an oxidizing agent, it causes the oxidation of other things. So that's why we say it's an oxidizing agent. So if something's in the presence of an oxidizing agent, it's getting oxidized. The agent isn't, but the thing in the presence of the oxidizing agent is going to be oxidized. That means that the oxidizing agent causes oxidation and takes those electrons for itself. And so it gets reduced. So it's a little, again, it seems a little backwards, but if you think about it, anything that causes oxidation to take place is going to take those electrons from the oxidation side of the reaction, and it's going to get reduced. So we say an oxidant or an oxidizing agent is something that causes oxidation to take place. Therefore, it gets reduced. And the same thing with a reductant or a reducing agent. That causes a reduction to take place. If a reduction takes place, that means that whoever was in the presence of the reducing agent got reduced. It received electrons. So what happened to the reducing agent? It must have lost electrons. It must have been oxidized. And so we say that, like, basically metals are reducing agents. Why are they reducing agents? Well, what happens to a metal in the presence of a non-metal? If I take a metal and a non-metal and put them together, what happens to the metal? We have some examples here, like we had iron
Is the
and
metal
oxygen. What happens to the metal?
Is the metal the reductant?
It is. What happens to it when it's in the presence of a non-metal?
It gains electrons, and then
The metal gains electrons? Who gains electrons?
I thought reduced when it gains electrons.
Yeah, see, it's confusing, right? You have to sort of stop and think about it. But if I have a metal, let's say magnesium, I got a ribbon of magnesium, and I've got it in the presence of oxygen, non-metal, and I burn the magnesium. What happens to the charge on the magnesium? What happens to the charge on the magnesium, on the metal? Does the charge go up or down? So when I react magnesium with oxygen, what happens to the charge on the magnesium?
Would it go up or is that wrong?
It goes up, right? Exactly, it goes up. It goes from what's the charge? What's the oxidation number on magnesium when it's in the metal, when it's in the ribbon?
I don't remember.
So magnesium, when it's by itself as a metal, it's only surrounded by other magnesium ions or metal atoms. Sorry, my bad. It's only surrounded by other magnesium atoms. So what's its oxidation number when it's in its most stable form?
0.
0, right. So its oxidation number is 0. And when it reacts with a non-metal, what happens to its charge? As it was said, it goes up, right? And in magnesium's case, it goes to +2. Always goes to +2 because magnesium ain't a transition metal. So we'd say magnesium gets oxidized. So does that make it the reductant or the oxidant? Is it the reducing agent or the oxidizing agent?
Reducing agent.
Exactly. Yeah, it's the reducing agent because it allows oxygen to get reduced. So the reducing agent doesn't get reduced itself. It causes somebody else to get reduced. The oxidizing agent doesn't get oxidized. It causes something else to get oxidized. That's why we say oxygen, that's where the term oxidizing agent comes from. Oxygen ain't getting oxidized. Nobody can oxidize oxygen except fluorine. Fluorine's the only other element that can oxidize oxygen. That's it. Because there's only one element that's more electronegative than oxygen, and that's fluorine. So fluorine can take electrons from oxygen, but nobody else can. So that's why it's such a strong oxidizing agent, because it oxidizes everything. So it always gets reduced.
Professor?
Yes.
So can you correct me if I'm wrong? So oxidized means loss of electrons,
Yep.
and reduced means gain of electrons.
Mm-hmm.
But oxidant means gain of electrons, and reductant means loss of electrons.
Right. Because as an oxidant, you are the thing causing oxidation to somebody else. That's the key part. If you put oxidizing agent or oxidant at the end of it, that means that you're not the one being oxidized. You're causing oxidation. You're causing oxidation of the other guy. So the easiest thing I find to remember is that oxygen that's an oxidizing agent. Does oxygen get oxidized? No, it does not. Oxygen gets reduced. And so oxidizing agents get reduced. Reducing agents get oxidized because they cause the reaction to take place to somebody else, not themselves. Yeah, that's the sort of the key thing to remember. So let's have a look at another reaction. So this time, instead of zinc, we've got aluminum foil. This is the reaction I like doing in the lab because copper solutions are pretty easy to make. Copper 2 is really quite soluble. Copper 2 salts are pretty soluble, easy to make, and you get this really pretty color. And you can just throw things in there and watch what happens. So in this instance, instead of zinc, we're throwing in a ball of aluminum foil. And look what happens. So this is the production of copper with an oxidation number of 0 on the surface of the aluminum. And you can see you get these like really weird stretched out tendrils of copper. It looks really weird. And why does this happen? Well, it happens because the electronegativity of copper is greater than the electronegativity of aluminum. So copper pulls on those electrons of aluminum more than aluminum can pull on them itself. And so if it pulls on them stronger, it's going to pull them away. And so aluminum will oxidize the copper. And when it oxidizes the copper, it reduces itself. So copper is the oxidant or the oxidizing agent, and aluminum is the reducing agent or the reductant. Okay, does that make sense to everybody? Hopefully.
I'm starting to understand it. It's just I have to keep repeating that to not get the
It is confusing. Yeah, when you think like oxidizing agents don't get oxidized. Why would that be? Yeah, just think that like oxidizing agents cause somebody else to get oxidized. Reducing agents cause somebody else to get reduced, not themselves. So that's what an agent does. Like basically copper's here minding its own business, staying oxidized until I throw the aluminum foil in. Jerome, please. So I throw the aluminum foil in. It causes the copper to become reduced. So it's a reducing agent. Because reduction wasn't taking place until I introduced it. Did you take Jerome somewhere? All right, so let's see what's going on here. Let's check in. So I've got 3 reactions here. And I would call we're going to learn that we call these half reactions because you can't have an oxidation without a reduction. If something's getting oxidized, somebody else is getting reduced. So we call these half reactions. So for A, is that an oxidation half reaction or a reduction half reaction? So A.
A would be the reductant. It's losing
Right, it is a reductant, that is true. But is that an oxidation reaction or a reduction reaction?
Oxidation?
Yes, it is, because tin is going from having an oxidation number of 0 to +4. Another way to look at it is if oxidation takes place, electrons are a product because they're being removed from something. So oxidation removes electrons. Remember, oxidation is loss. So you're removing electrons and sending them somewhere else. So that is an oxidation reaction. What about the second one? Iron 3 goes to iron 2. Is that an oxidation reaction or a reduction reaction? Could you take Jerome downstairs for a little while? Could you take Jerome downstairs just for a little while? I'll come and get him. Well, I've got Ferris saying it's a reduction, Malawan saying it's an oxidation. Which one is it?
I would say reduction because it's gaining electrons.
What do we think? Oxidation or reduction? I got 2 votes for reduction.
Reduction.
3 votes. Yeah, it's a reduction, right? So, number of ways to look at this. One is that, yeah, electrons are being gained. So, reduction is gain of electrons. The other way to look at it is just look at the charge. Look at the oxidation number. The oxidation number went from +3 to +2. It's gone down. It's been reduced. It was a larger number and now it's a smaller number. That's a reduction by definition. So what about the third one? Third one's a little trickier. Third one, we've got chlorine gas going into solution as chloride ion. Is that an oxidation or a reduction?
I would say oxidation because it starts off at 0, but then gains electron.
Okay. Anybody else? I don't know. A lot of reduction votes are coming in. Oh man, everyone's getting killed here. Reduction votes from everybody on the chat. Yeah, it's reduction. Right, because you need to remember chlorine is in its most stable form. It's bound to itself. And so if chlorine is bound to itself, it's sharing electrons with another chlorine atom. it can't pull electrons away from itself because one chlorine atom is exactly the same electronegativity as the other chlorine atom. So there's like going to be pulling on each other exactly the same. And so the electron cloud is going to be exactly the same around each one of those chlorine atoms. So its oxidation number is going to be 0.
And
But yes, go ahead.
what made me think that was the negative charge on the
Mhm.
right side? Wait,
Right, because it's gone from 0 to -1. It's gone down, right? Went from 0 to -1. It's been reduced.
Doesn't that mean, I thought that meant that we have an extra electron?
Mm-hmm. Yeah. So its charge has gone from 0 to -1. So it's been reduced. It's gained an electron. Each one of those atoms has gained an electron. That's why it takes 2 electrons to move from Cl2 to 2 moles of chloride ion, because 2 moles, 1 mole of electrons has gone into 1 of the moles of chlorine gas, and the other mole of electron has gone into the other chlorine atom in the chlorine molecule. So each one of them has received a mole of electrons and has become ions. They've been reduced. Yeah, we're going to take some time with this, believe me. Okay. So when we write these sort of reactions, like I said, there's always going to be 2 halves, because if an oxidation took place, the reduction took place too. Those electrons that we saw here, they're going to go somewhere and do something. These 4 electrons, let me go back. These 4 electrons are going to reduce somebody. These electrons had to come from somewhere. So for that reduction to take place, somebody had to get oxidized to produce those electrons. So they had to come from somewhere. So there's always going to be an oxidation side of a reaction and a reduction side of a reaction. So when we write them, we need to write separate oxidation and reduction reactions for each side to see where the electrons go, basically. So here is a reaction that takes place. So we have cesium as a solid. In the presence of fluorine gas, creates cesium fluoride. And this is going to be a pretty violent reaction because we know that cesium is in group 1, and group 1 alkali metals love to give away that electron. And who takes electrons better than fluorine? Nobody. So that's going to be a very violent reaction. So the cesium will lose an electron, form cesium ion. It's going to be oxidized. Fluorine is going to be reduced to form fluorine ions. But you can see that here I've got 1 electron and here I've got 2. So when I write the oxidation side, that has only 1 electron. And when I read the reduction side, that is 2. I'm going to have to balance those somehow. So basically that means I'm going to need 2 moles of cesium to make 2 moles of cesium ions and 2 electrons. That way they'll balance. And then notice when I add them together, I have 2 moles of cesium, 1 mole of fluorine gas. My electrons cancel because I've got 2 electrons on one side of the reaction. I got 2 electrons on the other side of the reaction. They'll cancel. And on the other side of the reaction, I've got 2 moles of cesium ion, 2 moles of fluoride ion, just like here. So when I add everything up, I should get back to the same reaction, okay? So we'll do a couple of those to show you how it works. But there's a lot of rules for doing these sort of things. So let's go through them. So oxidation numbers. How do you figure out what an oxidation number is? So we think about atoms as being ions, all of them, even if they're in a covalent molecule, because we want to identify them as their oxidation number. So we basically assume that if, like for instance, methane looks like this, right? 1, 2, 3, 4. Who's more electronegative, carbon or hydrogen?
Carbon.
Carbon. Carbon's slightly more electronegative than hydrogen. So what is the oxidation number of the hydrogens going to be?
+1.
Mm-hmm. So this one's going to be +1, +1, +1, +1. What does that make the oxidation number of carbon?
-4.
-4, exactly. And so we think of them as already having lost those electrons, even though they haven't really, because they're in a covalent molecule. They haven't actually lost those electrons yet, but we think of them as they have in order to determine their oxidation number. So notice that a combustion reaction is a redox reaction because carbon goes from having an oxidation number of -4 to, when it's in CO2, what's its oxidation number now?
+4.
Mm-hmm. Yeah, because this oxygen's -2, that one's -2. So the oxygen in the middle must be +4. So we think that, so oxygen's been like hella oxidized, right? It's gone from -4 to +4. So it's basically lost all 8 of its electrons, the whole octet. So that is a heavy duty redox reaction. So to figure these out, we just treat all atoms as if they're charged, even though they're not really, just to figure out what their oxidation numbers are. Now, uncombined elements, like I've been saying, any element that's in the presence of nothing else but other elements like it, other atoms like itself. So metals sharing metallic bonds, or diatomic elements in a diatomic element. Those, molecule, those are all going to be 0. Helium, going to be 0. All of the noble gases are going to be 0. Anything that's basically surrounded by nothing but its own atoms like itself, uncombined elements are going to be 0. Just like elements bonded to identical atoms. Same, basically, I think of them as the same situation because they're uncombined with anything else other than themselves. They're going to be 0 as well. So the most stable form of any element, basically 0. Now the oxidation number of simple ions, monatomic ions, sodium, potassium, chloride, fluoride, same as the charge. So sodium +1, calcium +2, aluminum +3, fluorine -1, and so on. If it's a simple monatomic ion, the charge is the oxidation number. That should be fairly easy to remember. Now, if you have a compound or an ionic compound, the overall oxidation number is the total charge. So if I have, just like I showed you before, if I have methane, and so carbon is -4, and the 4 hydrogens are all +1, the total has to be 0 because it is a compound. And a compound, by definition, has what charge?
No.
0. But that's the definition of a compound, right? It's a group of atoms that come together and have no net charge. Some of the atoms inside may be charged, but when you add them all up, 0. But if you have, like, say, a sulfate ion here, or a phosphate ion, or whatever, or ammonium ion, if you add all the oxidation numbers of all the atoms in that ion, they have to equal the charge. So for instance, sulfur and oxygen. In this situation, I got 4 oxygens. Oxygen's going to be -2. Unless it's bound to either itself or fluorine, it's going to be -2. That means, and there's only 1 sulfur in there. So that sulfur has to have an oxidation number of +6. Has to. Because the -8 from the 4 oxygens, when you add them to whatever sulfur is, the total has to be the same as the charge. So that's how you figure out the charge with polyatomic ions. It's really easy when it's oxygen based, because you know oxygen's going to be -2. And if there's only one other element in there, that has to be positive. Like for instance, with phosphate, what would be the oxidation number of phosphate phosphorus in phosphate, in PO4 -3. What's the oxidation number of phosphorus?
+5.
Exactly, right. Because I've got 2 times -4 plus something equals -3. So X has to be +5. So we can see that any time something's surrounded by oxygen, it's going to have a positive oxidation number. And generally, the more oxygen surrounding it, the higher your oxidation number is going to be. So neutral compound, got to add up to 0. So ionic compounds, again, really easy to figure out what the oxidation numbers are. Because we know, oxygen is going to be -2. And we did this one already. So iron's got to be +3. They have to balance each other. And again, if you see a Roman numeral, that's an oxidation number. Just stop right there. You automatically know if it's copper 2 sulfate, copper's got +2. If it's copper 3 sulfate, copper's +3. Iron 2, iron 3, anytime. So that's one of the reasons when you're naming ionic compounds, you give the number. So if you're doing a redox reaction, you can immediately start balancing it because you know what the oxidation number on that metal is. So you can start figuring out how many electrons are going back and forth. That, and you can balance the ionic compound. So here's some other general rules. Hydrogen is pretty much always +1 when it's bound to non-metals. So when it's bound to carbon, when it's bound to hydrogen, when it's bound to oxygen, bound to nitrogen, bound to any of the halides, chlorine, fluorine, bromine, so on, it's going to be +1. In a very few circumstances, when it's bound to a metal, it's -1. But that doesn't occur very often where you have hydrides. Most of the time, it's going to have a lower oxidation number than the non-metal it's bound to. On the other hand, it has a higher electronegativity than a lot of metals. So it can form hydrides, but mostly it's known for reacting with non-metals. So pretty much all the time when it's bound to non-metals, it's going to be +1. And that's what it's bound to most of the time. Now, oxygen, we've talked about oxygen incessantly. It's going to be -2, except when it's bound to fluorine. Fluorine can take electrons from it. So if I have oxygen difluoride, this fluorine is going to be -1. This fluorine is going to be -1. And so the oxygen has to be +2. Because fluorine really is the only molecule that can take electrons from oxygen. The other time it's not -2 is peroxide. So everyone's got some hydrogen peroxide in their medicine cabinet. And I've probably drawn hydrogen peroxide before, but it looks like this. Hydrogen peroxide is fairly unstable because this oxygen-oxygen bond breaks because both those oxygens are pulling on those that bonds. And what happens is they each take one electron. So one electron goes there, one electron goes there. And in this circumstance, so our hydrogen is +1. This hydrogen is +1. The overall molecule has to have a charge of 0. So that oxygen's -1, that oxygen's -1. Because basically what happens is they take that bond, they each take one electron from it. And so they don't become charged, they become a radical. So those are pretty much the only two times you're going to see oxygen with an oxidation number of anything but -2. And those aren't going to happen very often. Let's do a couple of these. So I've got HBr. What are my oxidation numbers on the hydrogen and the bromine? Anybody? Hydrogen and bromine. What are my oxidation numbers going to be?
Would it be +1 and -1?
Yeah, because hydrogen is going to be +1 if it's bound to a non-metal. Bromine is about as non-metal as it gets. So +1, -1. What about sodium oxide?
Would it be +1 -2?
Yep. Sodium is pretty much always going to be +1 unless it's sodium metal. When it's an ion, it's always going to be +1. And CH4, we just did that one, right? If you could remember. Carbon is a non-metal. And so when hydrogen is bound to it, it's going to be +1. +1, +1, +1, +1. It has to add up to 0, so carbon's going to be -4. And what about Al2O3? What is that? What do we call that? What's the name of that? What do we call that?
Oh, wouldn't the oxidation numbers be -2 and +3?
Sorry, I really can't hear you. What was that?
Sorry, my mic's a little broken. Wouldn't the oxidation numbers be -2 and +3?
Yes, that is correct. What's the name of the compound?
Aluminum trioxide.
Nope. Why not? Why don't we call it aluminum trioxide?
It's not a transition metal.
Isn't it aluminum oxide? Sorry, I didn't mean to interrupt someone.
No, it is aluminum oxide. Why don't we call it, so why don't we call it aluminum 3 oxide? Why don't we call it aluminum 3 trioxide? Why do we just call it aluminum oxide? First thing, why don't we call it aluminum trioxide? We don't say that. Why not?
Do we only do that when it's a transition metal?
Nope. That's when we use the 3. We don't use the 3 because aluminum is not a transition metal. It is always +3. Always, 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 always +3. So we don't include aluminum 3. But why don't we call it trioxide? I mean, there's three oxygens there. Why not call it trioxide?
Aluminum is always 3 plus, so there's no confusion. It won't be dioxide or monoxide. It will always be O3, so it's not necessary to say trioxide.
Yeah, but it isn't necessary for one important reason. You're right, it isn't necessary, but why isn't it necessary?
Is it
It's because of the kind of compound it is.
Covalent compound. I mean ionic compound.
Right. It's not a covalent compound. Because you remember, like covalent compounds, we can put together atoms in all kinds of crazy ways. But in an ionic compound, the charges have to balance. And so since aluminum is always +3, we know exactly how many oxygens there's going to be. If there's 2 aluminums, got to be 3. It can't be 1, can't be 2, can't be 4. It has to be 3. That's the only number it can be. Now, if it was iron oxide, we don't know what that is. That could be that, or it could be that. We don't know which one it is. So then you have to put the Roman numeral in there. But we only put like tri and mono and tetra and all that in covalent compounds. Okay? Because in ionic compounds, given the charge of the metal, you know what the charges of the nonmetals are. You know there's only one way for those things to go together. So let's look at sulfur here. Sulfur is one of those classic. Sulfur and phosphorus are 2 of the elements that change their oxidation number radically, depending on who they're bound to. So let's just look at sulfur. What would be its oxidation number in sulfuric acid? And again, you can just add up there's only one sulfur, so we can just add up the oxidation numbers.
Would sulfur in this case have an oxidation number +6, which
Yep.
would then mean that the SO4 ion would have -2?
Yep, exactly. Yeah, sulfate has a charge of -2. We pretty much know that because there's 2 protons associated with it. So yeah, so that would be +6. Good job. What about sulfite?
Would it be +4?
Why? Again, just add up all the oxidation numbers of all the other elements. So what's oxygen going to be? Oxygen's not bound to itself, and it's not bound to fluorine, so we know what its oxidation number is going to be. What is it?
-2.
It's going to be -2. Yep. Always, always, always. And so what's the oxidation number of sulfur going to be in this instance?
Would it be, I think I did that wrong before, would it be +6 for sulfur?
Also +6, right. Same.
Okay, all right.
It's the same. Mm-hmm.
Okay.
It's the same. Now, I've got sulfur dioxide. Actually, I make a mistake. This isn't sulfite. That's sulfur trioxide. There's no charge. So I made it, that's a molecule, not an ion. My bad. So sulfur dioxide. What's the oxidation number of sulfur now?
Would it be 0?
Why 0?
Because the oxygen was bound to itself. Oh, but never mind.
No, it looks like this.
So would it be +4?
Right.
+4?
Yep. Now we go to hydrogen sulfide. That's stinky, rotten egg smell gas. What would be the oxidation number on hydrogen of sulfur with hydrogen sulfide?
Wouldn't the two hydrogen atoms, wouldn't they have an oxidation number that added up to positive 2, and then the sulfur would have -2, so when you added them, the oxidation numbers would equal 0?
Man, you should be teaching this class. Yes, exactly. Yeah, H2S. So when hydrogen is bound to a non-metal, it's going to be +1. So I got 2 +1s. And then the whole thing has to add up to 0. So that sulfur has got to be -2. Very good. So you can see that sulfur changes its oxidation radically depending on what environment it's in. Generally, the more oxygen surrounding it, the higher the number. So let's just check. Yep, you got them all. Excellent. So yeah, my son actually just got these light-sensitive glasses. He got his first pair of glasses. So this is the reaction that actually takes place that turns them color. So you've got this thin layer of silver chloride on the surface, and the silver chloride you can see through it. But then when it's hit by UV light, an oxidation reaction, a redox reaction takes place. So who's oxidized and who's reduced? Which one's being oxidized? Which one's being reduced? So I got to vote for silver being oxidized. Chlorine being reduced. Chloride being reduced. Now remember, this goes from this side to that side. So these are the products because they're on the pointy side of the reaction, and these are the reactants. So just think of what happens to the charge of the reactants versus the products. So who gets oxidized, who gets reduced?
Chloride loses an electron.
Mm-hmm. And who gains it?
The silver.
Right. So who gets oxidized, who gets reduced?
Chloride gets oxidized.
Yep. Chloride ion gets oxidized to chlorine, and silver gets reduced from an ion to a metal. So you can see through silver ion, but of course, when silver is then reduced to the metal, you can't, it blocks a lot of the light, so your lenses get darker. So that's the reaction that takes place. So I was kind of hoping to have a little bit more time. So what I'll do is I'll introduce balancing these things, and then on Tuesday we'll go into it in more detail. So this is how so I show the batteries here because all of these batteries basically work on redox reactions. So basically usually you have two metals in a battery, and usually in the presence of something basic like a hydroxide or something like that, or an acid. In your car battery is lead with sulfuric acid. So yeah, you don't want to drink the contents of your car battery. And so the lead gets reduced and oxidized and reduced and oxidized. It gets oxidized when you start your car. It produces electrons to start your car. And then as it charges, as you drive it, it gets reduced back to the metals. So it goes from the metal to an ion in the solution, and then back to the metal, and then back to the ion in solution, and back to the metal. And eventually it will wear out when like all the lead is gone and it's all in solution, and then it won't work anymore. But it's a redox reaction. So here are the steps we need to do. So as I mentioned before, we need to split that reaction into two half reactions. One, reduction, the other, oxidation. Next, you got to balance, excuse me, balance those elements that aren't hydrogen and oxygen. We'll deal with those later, because pretty much all of these reactions take place in aqueous environments. So you're going to have water around to balance hydrogens and oxygens. Next, balance oxygens by putting water where you need it. So if I have 3 oxygens on one side, on the reactant side, and only 2 oxygens on the product side, well, I just put another water on the product side. Boom, I got my extra oxygen, no problem. I balance my hydrogens with protons. If it's an acidic environment, I add protons. If it's a basic environment, I add water. Now, and we'll get back to that in a minute. Then I have to balance the charge. So if I have +3 charge on one, like if I add up all the reactants and it adds up to +3, and then on the other side, all my products add up to +5, well, then I need to put 2 electrons on my product side so the charge is equal on both sides. Same thing if I have more charge, if I have a higher charge on the product of the reactant side, then I put electrons on the reactant side. Then I balance my electrons because it's a redox reaction. The number of electrons going in have to equal the number of electrons going out. So if I have 6 electrons on one side and I have 3 electrons on the other side, I multiply this one by 2 so that I have the same number of electrons going in and coming out. Then I finally add everything together. So all the reactants from both the oxidation and the reduction side, I add all of them together. And then I take all the products, everything on the other side, and I add all of those together and just cross out duplicates. And there'll be lots of duplicates. There'll be duplicates of protons, there'll be duplicates of water, and there should be the same number of electrons, so I can cancel those out as well. So I'm going to leave it there. And so on Tuesday, we'll do some of these together. I've posted these on Canvas. And so since we haven't really got into balancing these, I'm going to give you extra time on the last recitation because we haven't really explained it particularly well. So I'll give you another couple of days to work on that, because the last 2 questions were basically balancing redox reactions in acid-base solutions. So if you want to read ahead and give it a try, this has been posted. All these slides have been posted already. So, but we'll get into more detail on Tuesday. And so my 2 groups, I'm going to post the lab like in the next half hour or so, and then we'll do it this afternoon. Any questions? I know you can't wait to start doing these. These are fun, because, you know, nerds like doing stuff like this. Okay, so my 2 groups, I will see you at 1:10. Remember, if you have any questions, I'm pretty much available all day tomorrow. So just send me a note if you want to go over the exam or anything else. I'm thinking of having the lab exam at the end of next week. I just need to talk with AJ about that, but probably the end of next week. Yeah.
Is this going to be on a final, or are we going to have a separate exam for this?
This will be on the final. Yeah, we're not having another lecture exam. So yeah, you can count on like one question in the final being about this. But I'm going to go over it in detail, so don't freak out. Okay? Or go ahead and freak out. It's totally up to you. Anyway, I'll see my group soon. The rest of you, I'll see you either tomorrow or next week. Have a good weekend if I don't talk to you before then. Stay well, everybody.